Hi everyone, so here we are back again with the replication of Baller et al. In R, and we've spent the first two videos introducing R, basically doing the first bullet point on this slide, learning how to load data, export data, plot data, and construct spatial weights. And now we're going to move into this a more substantive replication of Baller et al., beginning with maps 1 through 4, the LISA cluster maps. So basically, if we go back to R, in the first video, I demonstrated how to open R, install packages, open the packages with a library command, and then load the data. And now we're going to open the R script, moving up here to the top left, that contains the commands to generate the LISA cluster maps. As I mentioned earlier, the second R script contains all of the material in the first R script. The third R script contains all of the material in the first and second, and so forth. So if you just open the second R script, Replication1B R2, you should have all of the material from the first one. You'll see it begins with the introductory material and the acknowledgments, quick outline, and all of the helpful commands from before, etc. So you could just open the second R script. You have all of the earlier material. If you made any notations using the pound sign in the R script and then saved it as your own R script, which I encourage you to do. You should use these R scripts and manipulate them and change them. If you find something that's online that's really useful and would be productive for the rest of the class to learn, please share that with us. And you can add your own notations, comments, etc. in these R scripts and then save them under a new file name for future reference. But anyhow, all of the material from the first session is here. You see here's plotting. Now here's the section on generating spatial weights. And then finally detecting spatial dependence. So all of the commands that we executed in the first session have been executed. All of the data in memory is still in memory in the R workspace. So now let's go through and generate some of these results from from Baller et al. If we wanted to, we might want to pull up Baller and just have it handy. You'll remember that in the maps 1 through 4, we're reporting the local indicators of spatial autocorrelation, but there was also some global spatial autocorrelation that was reported, right? So that here under results on page 573, you see that the coefficient for Moran's I, the Moran's I statistics, is a global indicator of spatial dependence, are 363, 420, 371, and 372. These are all statistically significant. So let's just see if we can replicate at least 1960, and then you can play with the rest of the data. So moving back to our R script, the command here for generating Moran's I is the Moran Test and then the Moran Plot. We did both of these also in Geoda already. As I noted before, we've attached the data already. If you wanted to just double check, you could say attach nat data. That was the data frame part of the nat shapefile. So you could just highlight that and then hit Control R. It attaches that data. Now we don't need to specify the data set every time we refer to a variable. So here's a variable for homicide rate in 1960. If we did not have the data set attached, we would have to say nat data $, homicide rate 1960, or from the shapefile nat homicide rate 1960. But since we have it attached, we don't need to go through that extra step. That's a nice little shorthand, and we can just run the Moran Test command. This is the function to find the Moran's I value. We're going to execute it on this data set and with these spatial weights. Right? This is the 10 nearest neighbors, the list object that we created before. So let's hit Control R. It takes a little bit, but there it is. So here's our statistic, 0.3589. That's basically 0.36 or 0.359, you could say. And it has a p-value that's very, very small, so this is statistically significant. I can't remember what the value was for 1960, but so there's 1960, 363, 358. It's very, very close. They should be the same. We're not using the symmetric one, which added some connections. Was this the symmetric one? That might explain some of the variation, but let's just go back and check. No, it's NatSim was 10b, so this is just your list object. Well, in any case, they're very close. If anybody wanted to investigate what the source of that difference might be, that would be interesting to know. You could also generate some different tests. Hang on just one second. One possible explanation is that the sub-options for the command may be different, or they may have specified some other options. They did not use R, by the way. They used a program, I believe it was SpatStat at the time, or SpaceStat at the time. We'll talk about that in class. But they may have been operating under different assumptions. We can explore some of those possibilities by looking up the documentation for Moran Test. Again, this is a shorthand for looking up the help menu for a command. So question mark Moran Test. Let's just hit return there over here in the workspace. It should call up a web page. So here it is, search results. And this is the generic syntax. So they may have been operating under assuming some normal distribution. That should only affect the significance. The zero policy refers to how islands are treated. So if there are some counties that are not connected to other counties, that shouldn't be the case. But if this is treated as null, then well, the two options here is that islands can be treated as having a value of 0, or they can be ignored altogether. That obviously creates some different results. So that might have, they may have been treating islands or some other feature of the data differently. Anyhow, that would help explain this very small difference in the Moran's I. But in general, we have a very close value, 363 versus basically 359. So that's the Moran test. We can explore some of these other assumptions. I believe the default assumption is normality. That is, you're comparing the distribution to a normal distribution. You could explore a randomization assumption by highlighting this and running the test. You're getting basically the same results reported in a slightly different manner. And then we could explore one other option. Hang on just one second. So in short, these are a couple of different options for extracting Moran's eye. Again, you could search the help menu to look at syntax options, but you basically have a randomization option or a normality option. One other interesting way of presenting Moran's eye and of generating significance tests is to do a small permutation analysis. So basically, with this command here, you're doing Moran's Monte Carlo simulation. So you're generating the statistics for inferring significance by simulation. You're running basically 1,000 iterations or permutations in this simulation, and you would get different, because this is a random shuffling that's taking place to generate the statistical significance here. You're going to get slightly different results each time, unless you set the seed here at the beginning, this sort of baseline value at the beginning. But if you follow this series of steps, so if you highlight all of this, set the seed, run this simulation, hit Control R, we generate the Moran's eye statistic, 0.359, see the p-value, 1,000 simulations, and then following the Anselin R workbook, the reference book that I mentioned earlier, we can graph these results to sort of better understand what is taking place. So here I've copied in some notes from Anselin. The results of the simulation are assigned to an object of class H test, so that's the name of this object now. So you can print it to reveal its contents. That's what I did over here. One item in the list is a vector with the computed statistics for the permuted data set. This is contained in the item res. So that note that the observed value of Moran's eye is the very last element. So if we print that vector, you can see that the very last item is the actual observed value, and these are all the simulated values, the other 999 simulated values. So to graph this, we could present a histogram first. So there's a histogram. We can generate a zero line here, and we can add a density plot. Sorry, I'm combining some graphs from Elizabeth Root with some graphs from Anselin. So let's just start with the commands from Anselin. So this is again borrowed from the Anselin R workbook, pages 20 and 24. So we're creating a density object. We want to remove the very last value, right? The actual value. So we're going to create this object that's the earlier vector that we created from the simulation minus the very last value, the observed value. So now we have this density object that consists only of the simulated values. We pass it through this density function. We don't specify any of the sub-options that you could. You could do a search for this function as well to better understand it. And then we can plot it. So this is the density function. I've tinkered with the axes ahead of time a little bit to make sure that it fits nicely within the frame here. And we'll add the histogram. As you can see, the histogram, the density function sort of smooths out the corners there. And then this is our actual value, right? So 3.59, 3.6 thereabouts. This is our actual value. This is our distribution. Thinking back to basic inferential statistics, right? If we were inside of 95% of this distribution, right, then we wouldn't be able to claim any statistical significance. If say we shifted this blue line to inside 95% of this distribution, then we wouldn't be able to say that our Moran's I value was anything that we'd expect to find other than by chance or at random. But we are entirely outside of this distribution. So that is why the statistical significance was so high. If we go back to our earlier p-value, that's why this value of Moran's I is so statistically significant. So again, all of that work just to be able to say that the distribution of homicide rates across U.S. counties in 1960 does not appear to be random, right? It is not spatially random, or what some people might call CRS, right? Completely, or CSR, completely spatially random. So let's move forward with the maps now that we've established the Moran's I. So Moran's I, again, allows us to detect spatial dependence at the aggregate global level across the entire sample of spatial units that we're examining. And now we want to generate the local values of spatial autocorrelation, or the local indicators of spatial autocorrelation, which we shorthand as LISA values. I'll start those in a second short video.